Welcome to today's deep dive. We're looking at a really fascinating video from Anastasia in Tech. It breaks down the terrifying math behind the new semiconductor war between TSMC and Intel.
Yeah, it's a massive shift in the industry right now.
Right, so our mission today is to figure out how these two titans are taking, radically opposite paths to save computing. Because the basic laws of physics are just starting to break down, right?
Exactly. I mean, it is the absolute definition of hitting a physical wall. For decades, the industry just relied on this 30 to 50% speed boost every single generation.
You shrink the transistor, you get a massive upgrade.
Right, but at this new angstrom scale, we are fighting tooth and nail for just a 6% improvement.
And this is happening at the exact moment when AI is demanding, 100 times more compute power?
Yeah.
So you mentioned the angstrom scale. What is actually happening to the physics down at that microscopic size?
Well, at the single-digit nanometer scale, electrons basically just ignore the rules. They start tunneling through barriers that they're, never supposed to cross.
Oh, wow. It's like trying to keep water in a bucket, but the bucket is made of chain link fence.
Yeah, that's a great way to put it.
The basic engine of our technological progress is literally leaking. So how do they fix it? I always just assumed they could, print bigger chips to get more power. Why not just make an enormous processor?
So that comes down to something called the reticle limit. The machine that projects the light onto the silicon is physically capped at a tiny rectangle. It's exactly 26 by 33 millimeters.
Okay.
That is your stencil, and you just cannot print an infinite area in a single pass.
Wait, so it's like trying to paint a massive sprawling mural on the side of a building, but you're only allowed to use a tiny fixed-size rubber stamp.
That is exactly it.
You can't make the stamp bigger, so you have to perfectly stamp it 100 times to make the picture.
Exactly. And that physical limitation completely changed TSMC's strategy. They actually stopped trying to build one single denser chip.
Oh, really?
Yeah, instead, they are building what you might call mega chips. They take different components like compute chiplets, memory, and they stitch them all together.
But wait, if you stitch a system together like that, doesn't getting all those distinct pieces to talk to each other become a total nightmare? I mean, traditional copper wiring generates way too much heat at that scale, right?
It does. The challenge entirely shifts from computation to communication. Moving massive amounts of data without melting the entire system, that becomes the primary bottleneck.
Makes sense.
That is why TSMC is heavily prioritizing advanced packaging over, shiny new toys. They are actually refusing to adopt the newest, most advanced lithography machines right now.
Right, you're talking about those high-NA EUV machines, which cost $400 million a pop. So TSMC is skipping them to focus on flawless operational execution. They're basically building a mega city with the tools they already have.
Yeah, exactly. But meanwhile, across the ocean at Intel's D1X lab in Oregon, they are taking the exact opposite approach. Intel is trying to punch straight through the limits of physics. They are adopting those $400 million high-NA EUV machines.
Because those machines use a larger optical lens to focus extreme ultraviolet light, right? Which lets them print much sharper, finer patterns on the silicon.
Spot on. They are trying to invent a fundamentally better brick for the foundation. And, it is not just the lenses.
Yeah, I was reading about this PowerVia tech they're implementing.
Well, yeah. PowerVia physically separates the power and the signals. So signals stay on the front of the silicon, and power comes in from the back.
That makes so much sense. Traditional chips are like a city where power lines and heavy traffic are sharing the exact same narrow streets, which causes massive congestion and interference.
Exactly, and moving the power to the back clears the roads for data. But on top of that, they are using directed self-assembly.
Which is like microscopic Legos that use chemistry to just build themselves the second you apply heat. But, I have to push back here a bit. Aren't they changing way too many variables at once?
It is a massive risk.
Right. If one thing breaks in that whole chain, how do you even isolate the problem?
You've hit on the biggest issue. It is an incredibly risky, non-linear gamble. The golden rule of semiconductors is to never change too many things at once.
But they're changing everything.
They are. However, Intel might actually have a wild card here. There's this massive factory project called Terafab.
Okay.
It aims for the output of 25 advanced fabs in one integrated system, and it is tied to companies like Tesla, SpaceX, and xAI.
Wait, let's unpack that. Why does bringing in car and rocket companies help a chip manufacturer?
Well, traditional chip making is cautious and slow, but Tesla and SpaceX, they use this agile, blow it up and try again mentality.
Oh, right.
Applying that rapid iteration to semiconductors could compress decades of Intel's lab research into just a few years. It gives them the massive scale required to make this complex technology a reality.
Wow. So if you were banking on the next generation of AI tools, your entire future basically relies on how this plays out.
It really does.
It all depends on whether the market rewards Intel's aggressive leap or TSMC's flawless, low-risk execution.
And you have to remember, corporate customers usually buy certainty over raw performance. TSMC delivers certainty at scale.
Right. But that raises an uncomfortable question for you to think about. If the market punishes Intel for taking this massive necessary leap and rewards TSMC for playing it safe, what happens to the pace of human innovation? Like, if we stop trying to punch through the wall just because the math gets terrifying, do we end up trapping ourselves?
Yeah.